Thanks to the ASHRAE grant received by a capstone team at Concordia University, Montreal, a proposed energy-efficient heat exchanger would be designed, manufactured, and tested. This would allow the students on the team to learn more about HVAC systems and their potential for improvement by reducing energy consumption, all while keeping the environment they are used in as comfortable as before. The team first observed a rising issue of carbon emissions created by HVAC systems within your average typical office building. HVAC systems were responsible for the largest element of carbon emissions within buildings, rated at 55% of the building's total carbon emissions. With the rising issue of climate change affecting how inhabitable planet Earth is, the team saw an opportunity for improvement. To solve this issue, the team sought out a novel combination of a typical HVAC system and the natural properties of phase change materials. Phase change materials, also referred to as PCM, are everyday materials capable of releasing and absorbing thermal energy when changing phases. The team's proposal would also include the recent technological advancement of active chilled beam systems, a system capable of extracting and transporting heat effectively through the use of both natural and forced convection. Typically located on the ceiling, the chilled beam would either push air into the room to circulate the air within, or simply have hot air rise and cool air fall. Coiled copper pipes with running water would then either absorb the heat or release heat depending on the desired room temperature. The idea behind the team's proposal was to effectively extract the heat with the chilled beam and store it into the PCM, or extract heat from the PCM and release it into the room. After thorough research, paraffin wax with a melting temperature of 21 degrees Celsius was selected so that the heat transfer could be done at a comfortable room temperature. The team designed a test stand which incorporates a heat exchanger where the PCM is placed in, and a loop capable of simulating the heat transfer created by the chilled beam. Here's how the loop works. The loop starts with a water inlet directly connected to a water pump. The water would then pass through pressure gauges and flow meters. It is then pushed into a helical heat exchanger the team designed. The water would pass through the helical copper tube, while the PCM stays put within two acrylic tubes that form a shell. The water then passes through more sensors, including thermocouples that measure the water temperature and the PCM temperature. The loop includes an air release valve to allow the air to escape. The water then either enters a chiller or a heater. These two will allow the users to simulate the heat transfer created by the chilled beam. Finally, the water comes back to the inlet and the water pump to repeat the same cycle. While there were obstacles to overcome, the team was able to perform tests and gather results. These would then be compared with simulations created on ANSYS, as well as preliminary calculations made by the team. After analyzing and comparing the results of the test stand, the team achieved the temperature control desired, all while keeping the energy consumption very low. Thanks to the ASHRAE grant, the capstone team was able to achieve their goal and document the journey so that others may pick up in their footsteps. As well, ASHRAE invited the team to the 2023 ASHRAE Winter Conference, which allowed the team to learn more about the organization itself, network with peers, experts, and important figures in the industry, and win the Certification of Achievement in regards to the Undergraduate Program Equipment Project. The team is deeply grateful for the opportunity given by ASHRAE and its continuous effort in aiding students to learn more about the HVAC industry. The team would also like to thank the faculty at Concordia University for providing the facilities and project aid.